Welcome back, everyone. Hopefully the first week went okay. Let's begin the second week. The basic goal here is to solidify the foundation of calculus. For that purpose, let's use the other textbook, Calculus by Michael Spivak, which goes a little bit deeper and brings in more rigor than our main textbook by Lang. Consequently, it is a little bit more difficult, but at this level, I think we can handle it. Basically, we're going to cover chapter 1 of Spivak, and it's about the properties of real numbers. Okay, here we go. It is possible to classify the properties of real numbers into these three: algebraic properties, order properties, and topological property. First, the algebraic property, and these are about two natural algebraic operations in the set of real numbers: addition and multiplication. The subtraction and the division are their inverse operations, so they are not standalone operations. These two are the standard natural algebraic operations. Okay, here are some axioms associated to addition: associativity, the additive identity, the additive inverse, and the commutativity. Next, four about the multiplication: associativity, multiplicative identity, multiplicative inverse, and commutativity. And finally, both of them together, the distributivity. These 9 axioms summarize everything about the algebraic properties of real numbers. I have some comments here. Let's take a closer look at 1.2, the additive identity. In this axiom, we were given the existence of an additive identity, but here's a lingering question: how many are there? Well, there's an existence given, so there's at least one, but what if there are more than one? That's going to be a bit of a problem, but luckily we can actually prove that there is one and only one. Let's suppose that there are more than one, O1 and O2, that satisfy this one. Then it is possible to prove that they are the same, like this. Let's observe that O2 is an additive identity because we assume both O1 and O2 are additive identities. Adding an additive identity will not change anything, so O1 is equal to O1 plus O2 because this one doesn't change anything. Likewise, O1 is an additive identity, so it doesn't change anything, so O1 plus O2 is equal to O2 because this one drops out. As a result, what do we get? O1 is equal to O2. These two are the same. So if we have two additive identities, they are the same. Consequently, we have one and only one additive identity. Consequently, we can name it as 0. And that's how we define the number 0. Next, additive inverse. Likewise, we can prove the uniqueness. For given real number x, the existence of an additive inverse is given. There is a certain real number y, so that x plus y is equal to y plus x equal to 0. Fine. What if there are more than one? Well, as a matter of fact, we can prove that there is only one. Let's suppose there are two additive inverses of x, y1 and y2. We can prove that they are the same, kind of like this. y1 is equal to y1 plus 0. Why? Because 0 is the additive identity, so it doesn't change anything. Now, y2 is an additive inverse of x, so 0 is equal to x plus y2. And then we use the associativity. We change the order of addition through this grouping, and we end up with y1 plus x inside the parenthesis. And please note that y1 is an additive inverse of x, so that's equals to 0. This one is equal to 0. We get 0. Adding 0 doesn't change anything, so we end up with y2 in the end. End result, y1 is equal to y2. Consequently, if we have two additive inverses of x, they turn out to the same. Therefore, given x, there is one and only one additive inverse. Therefore, we can name it. We'll define it as negative x. That's how we define negative x, and adding the additive inverse is the subtraction. Now, can you establish the same thing for multiplications? There's one and only one multiplicative identity using the same trick, same argument, except that you have to use multiplication in place of addition. You should, because I assigned it as a homework problem. The same thing for the multiplicative inverse. Yes, you have to do it because I assigned it as a homework problem. You did exactly the same thing just now using addition. Change all those to multiplication and that's it. In short, we're done with all those algebraic properties, which can be summarized in the next section like this. We have algebraic operations, addition and multiplication, all right? And then we have all these properties. This time I took a bit of a shortcut because we already proved that there is one and only one additive identity, 0. So we used the uniqueness as well here. And also there's one and only one additive inverse for given x. So we used negative x notation. For multiplicative identity, again, there's one and only one in R star. By the way, what is R star? It is all real numbers except for 0. That's standard notation, by the way. Putting star usually eliminates 0, everything else. So if you have 0, then 0 doesn't have any multiplicative inverse. There's no such thing as 1 over 0, that's basically it. And yes, okay. Alright, we just reviewed the algebraic properties, and okay, let's go over to order properties. The way our textbooks did was to establish the positivity first and then to prove all those properties of inequalities, but I thought it was overly complicated, so I'm compromising a little bit. Instead, let's set up some axioms regarding inequalities and define the set of positive numbers as the set of all real numbers strictly greater than 0 instead of going the other way around. Let's follow my convention here. This is my notebook, my class. Here's the first axiom, trichotomy. For any pair of real numbers x and y, one and only one of the following holds. X is less than y, or x is equal to y, or x is greater than y. Some people call it comparability. For any pair of real numbers, we can compare the size of these two. Next, transitivity. If x is less than y and y is less than z, then x is less than z. Using these two, 1 and 2, we can arrange all the all the real numbers on a certain line, which we call the number line. Smaller numbers go to the left, larger numbers go to the right. Transitivity is essential because if you have even larger number, it goes further to the right, never coming back. And then comparability, this trichotomy is important because we don't have any two-dimensional situation, or we cannot find any place for this number, those kind of things. Every number has its place. By the way, let's have a little bit of digression here. The topological property of real numbers tells us the other way around. For given any point on a line, can we assign a real number there? And the answer is yes. So this algebraic property, and especially the order property, 2.1 and 2.2 particular, tell us that it is possible to arrange all the real numbers on a line. topological property says if you do that, we just fill up entire line. There's no gap. And we have the concept of this number line, and we can draw things, we can do the measurement and things like those. We won't have time to discuss any more about topological property in week 2, so let's leave it at that. And let's come back to the order property. We talked about the first and the second. Now let's go over to the third property. The inequality preserves the addition. If x is less than y, then x plus z is less than y plus z for any real number z. Good. Now how about the multiplication? If x is less than y, then is xz less than yz for every real number z? No, not really, but it's true for every positive real number. If z is positive, then xz is less than yz. Now what if z is negative? We can actually prove that we have to flip the direction of the inequality using all the properties that we discussed before. And those and many others will appear in these applications 1 and 2. And we're going to talk about those in a separate video.